have a cooperation so present in his students' work. Well, the motivation of this work is basically because in Brazil it's basically the transport mode of Brazil is the roads, is highways, for everything, for cars, for public in general, for materials, and you have a lot of accidents. That's a huge impact in Brazilian highway accidents. And some recent studies estimate that road crashes cost around 3% of the Brazilian GDP. It's a high value for a country. So we must try mitigate this scenario. And one of our goal here is evaluate empirically how spatial segmentation and temporal resolution affect the forecasting of crash counting in these classical algorithms. So what's the problem statement for us here? During the how federal highway policy in Brazil, here in the acronym is in Portuguese, Polícia Rodoviária Federal, which means Highway Federal Policy, turn the how data into useful information to feed several algorithms of classification algorithms. So you define the spatial and temporal granularity of the analysis, handle the biases of the traffic exposure variation, and adopt some protocols compatible with real operation use case. So in this, you're asking, how do segmentation strategy and temporal granularity affect both effectiveness and efficiency of established forecasting model? So this is more a work of feature engineering than a new model at all. It's more about feature engineering of the raw data of the PRF. So our main contributions, what we did here was, first of all, instead of just segmentate the highway into fixed length as literature, which usually just segment into 1 kilometer by each segment, we use the socioeconomic segmentation, which means we use the series around the highway to characterize where the accidents occurs. Some experimental framework, you made experimental comparison of spatial temporal and measure the effectiveness and efficiency of this algorithm in this kind of segmentation of the highway. And we discuss the trade-off of the accuracy and performance. Overall, usually, normally people just use some prediction models to try to estimate the number of crashes, and usually use just spatial representation in a fixed length. What we did different is that we use the socioeconomic segmentation. There's a lot of folks now using LLM as everything that still nowadays there's no so good result in this kind of data for prediction to these days. And now position our work in literature, instead of use just deep learning models, you use classical models, which is good, which is the computational cost is lesser than deep learning approach, and you use socioeconomic segmentation instead of fixed segments as the majority of the rules. So what's the data? Now, for those that don't, basically here almost everyone knows Brazil, but what is highways 040? It's one of the main highway in Brazil because it goes from Brazil capital, until Rio de Janeiro, which is the port, where is the main port, the main place to exportation and import things from the interior of Brazil. And passing through Minas Gerais, that's the third GDP state in Brazil. So it's a really important highway. Most of this highway is not duplicated. It's just a single lane and going back. So it's a dangerous highway besides its importance. We have data from 2017 until to 2024 with more than 26,000 crash records. As attributes, you have date and time, and the highway, municipality, geographic coordinates, primary detail codes, crash type and severity, time of the day, where some counts like people who was involved, how many was injured, how many deaths happened in that kind of accident. Just a point of deaths is just for deaths that occurred at the moment of the accident. Sometimes people die some days before after the accident, and this is not counted here. So you make some cleaning before, and then create new variables and use processed some variables that are high cardinality, like traçado is like the path where the highway is doing is the path of the highway coordinates. So this was decomposed. We constructed calendar attributes like holiday or no holiday, weekend or not a weekend, because this has a high, it's so that this has high influence in this type of accidents. So we evaluate with and without this calendar to measure where these affect or not affect the data. As the models, we use the classic models. Why classic models? Because classic models just works and it's computationally less expensive than deep learning models that doesn't create better results at all. So you the classical random forest, extra tree regressions, and Sarimax. It's the computational cost of Sarimax is lesser than random forest. Yet we saw that here, and it basically works because you have some when the data has some kind of temporal dependence. It's a time series like this one. Sarimax usually works and outfits the classic models always. And we use the same in the classical hyperparameters, but we did some tests, so ablation tests to decide which one worked better. So, going to the segmentation protocol, we just incorporated the municipal variables. For instance, the city, because the highway in Brazil is not like here in Europe where doesn't cross the city. In Brazil, the highway crosses the city and becomes part of the city in some points. So we incorporated this information in the data. Okay, this is a point where there's a lot of population around the highway. This is a path where you don't have so many populations, just crossing some mountains in the path. And you segment and you create this divided into 18, 24, 30, and 36 segments. What we want to see is how is the influence of the size of the segment in the classification, in the forecasting of the crash accidents. So for this, we create from 18 to 36 segments. The temporal resolution, we also evaluate, okay, let's see the resolution monthly, just taking the data monthly or weekly. It's of course it's obvious that when you see the data weekly, you have less accidents, so it's probably less you preserve some variations like routines, the weekly routines that the monthly doesn't preserve. But when you aggregate the data monthly, of course you have a lot of more accidents, and you can see the annual seasonality. For instance, Brazil, the summer vacations is in January, so you have more accidents, or more plans to have more accidents in the highways in January than in April. That is a common month. So we evaluated these two scenarios: granularity, the temporal granularity, and the segments granularity. We use it as test 70 to 22, validation 23, and test 24. There's a limitation here because everyone knows that between 20 and 22, you have the pandemic time. So there's some kind of limitation already that you saw after everything is done. Okay, but maybe 20 and 21 have some kind of problems in the data because of the pandemics. We measure if the variance explained, the square, mean absolute error, and root of mean standard error. We also studied the total execution time to understand the computational costs of these algorithms error. So going directly to the results, what we see when you look for the data monthly, considering weekend or no weekend, is that SARIMAX, which is the appropriate model for time series, has, sorry, the YX was in Portuguese and I just saw this last minute. And we have the SARIMAX with a low mean absolute error, while regression as well has a low, but 4 times greater than the SARIMAX. And another important observation is when you increase when you decrease the size of the segments, that means I increase the number of segments, our algorithms tends to be better, because how small is the segment, better the algorithm converges. Removing the calendar doesn't create a high effect. Indeed, what we saw is, doesn't matter if it's a weekend or if it's holiday, the increase it a little bit, approximately 5%, but it's not enough to say, okay, there's a clear difference between holiday or no holiday, weekend or no weekend, to separate the data. But when you look for granularity weekly, things change a little bit, because we have some, the R square goes down, and every algorithm seems like the same when you create the same of segments. Why this happened? Just because I'm increasing a lot the granularity. Maybe now it's weekly, that the dynamic is weekly is totally different for the dynamic monthly, and then the algorithm is works out almost as the same with high number of segments. However, when I look for efficiency, we have this almost the same efficiency, but with a cost with 10 times greater for SARIMAX. So there's a clear problem here, because you sometimes you don't have a clear winner, because at some point SARIMAX is better, at some points random forests have the same results, but when we look for computational costs, the execution time of SARIMAX costs a lot compared with random forests, random trees. We analyzed statistically the difference, and what we saw was SARIMAX is clear better algorithm when you look, especially monthly. You have significant better. We can say about the trees, the random tree or extra trees, the algorithm based in trees didn't show significant difference, but computational costs showed a clear difference as well between the algorithms. So the model are best as complementary highway for planning. They are not competing among themselves. SARIMAX has a higher accuracy, and it's better for long periods, like monthly periods. And similar methods like the extra trees just create some complexity, but sometimes you don't need them. And including calendar variables tends to improve the fit, but we didn't show a clear and statistically significant difference between consider or not the calendar variables here when evaluating these models. Some limitations, of course, we're talking about just BR 040, which may limit generalization. We can say the same for the highways. The PRF database just now is putting more data about other highways that we can do as future work, analyze together several highways in Brazil. Most of them has a lot of accents, so unfortunately, there's no problem of data of crashes in this kind of highways in Brazil. But you don't have data about the traffic exposure. They have no idea how many was the traffic there, how many cars passed there, which may be complemented by data from some kind of tolls. Some of the 040 has some tolls in some parts of, especially near Brasilia. But this data usually is not open, and you don't have the idea of how many the traffic, especially daily, weekly, or monthly cars, vehicles pass through there. And we need to improve this data with more data to have a model that's more sensitive to Brazilian politicians' interventions. So in conclusion is that we analyze the protocol segmentation and temporal granularity of the data. We realize that, analyzing weekly is more assertive than monthly, but calendar variables is not so important as everything the common sense used to say. And the SARI-MAX, which is a classical time series algorithms, works well for this kind of problem. You don't require some deep learning or some expensive to this kind of modeling. So that's it. Thank you for. I hope I did time because
yes, good time. So questions. Some questions. Thank you, Minister, for the conversation. I'm just curious about how to use this solution to other, if it's possible to use in other roads, for example, consider Brazilian areas. And if you think about other data, like, for example, rain.
Yeah, on some time ago, some year time ago, I had a project with the Brasilia City Hall, Vitória City Hall, where I get the data from Waze. With the data of Waze, I have all conditions of traffic, all conditions of how many cars are in that time, the moment. But this is located for cities. You don't have this kind of data for highways, and maybe you can enrich a lot the data if you have some kind of partnership with some apps like Waze, Google Maps. But this is not so easy to get, especially you can do this with public data. But yes, of course, we can enrich a lot if we have some special data of the real-time traffic of that moment of the what happened, that what's causing the accident. It's maybe a lot of traffic cause people get angry and do some stupid thing that's in the highway, which is my bet. But yes, of course.
Any more questions? Oh, next one or two. So thank you for very interesting. I was just trying to understand what is your goal in terms of what you're trying to optimize, because you mentioned at the beginning efficiency. So what exactly do you mean by efficiency when you're trying to segment a road? What is the most efficient? How do you measure efficiency?
Yeah, efficient. Just one point. Efficiency here is just execution time of algorithms. Okay, it's just about that. But efficiency in terms of operational
of the result, of the end result. How do you know that certain segmentation is better than another?
Yeah, at that point, the segmentation. What we see is increase the size of segment. Sorry, decrease the size of segment. In other words, increase the number of segments. If you are more assertive in terms of forecasting, but as well you create a lot of too much more data, too more variables, and which increase the execution time. I don't know if I get your question exactly.
Yeah, maybe. I mean, I was because if you are expecting this to be actionable in the sense that you can do something about it, right? In the end, what you want to understand is that there may be things, specific things that are causing more accidents, right?
Yeah.
So it seems like you're focusing more on calendar days, there's more traffic or something like that, and looking at the road as a whole, essentially. But normally it's more about the road itself, right? Because there's these points where there's lots of accidents and you want to identify them and so on. And so that wouldn't really be a time series, right?
Yeah.
That would be a different way of looking at data. So I was just trying to understand why you take this segmentation approach, and
but
just you know it's the right one.
Just a curiosity things, because in 040, especially in this part, this is I didn't measure it, but it's a common sense for us that live here. This is one of the most dangerous parts. So you know that a lot of crashes occurs here, and these are a high urban area or close to urban area. It's like people arriving at Belo Horizonte from Brazil, from Rio de Janeiro, and you know that most of the accidents are concentrated here because it's a critical part of the BR. So you're right. Maybe you can say you can already segment the hour. Just think about this place, closer the places where you know more crashes are occurring. But this would be another way of segment the.
All right, thank you very much.
Thank you.
So next presentation, we have Diego Diaz. Diego Diaz. Not in Spanish way.
Diego Diaz. Exemplo de ser alguém Diego, I need to say Diego. Diego. Yes.
Não, a gente pode ler esse cara, mas eu não sabia. A gente é muito bom.
Não, mas ele tá bagunçado ali, ó. Tá errado. Então, mas. Ah, não tá.
Não faz nada.
Deixa eu duplicar a tela.
Estava.
Não tá mais.
Não.
Ué, mas por que ele está mostrando as duas ao mesmo tempo? Tá mostrando a mesma coisa aqui? Não. Pode ser sim, também, sem rotação, por favor.
Não, mas vai ter.
Mas esse é um negócio diferente.
Não, pode ser sem rotação também, não tem precisando. Ah, é verdade, tenta aí, ok.
Só não tem horário, o internet de nações.
Não, então só se não está deixando escolher a tela. Entendi, mas é isso mesmo. Tem que ser entendido, não pode ser duplicado. Você tem que passar no resto. Isso, agora sim.
Você vai perder a paciência, mas faz o besteira.
Okay, sorry, I'm sorry. Hello, everyone. Now I promise that's the last one I want to present. First, the third and the last one. This work was led by my student, Victor Kwan, undergraduate student also, a student from the statistics department, and I was his advisor, and we have here some other professors for Computational Science, statisticians, and so on. Also developed this collaboration with UFJ, UFIS, and Unifesp. This work has got motivation, the post-stroke rehabilitation, that increasingly leans on motion capture and extended reality to make the exercise engaging. So we use a natural interface like IMUs and Kinects and media pipes, for example, to use the whole body, the patient's body, into the controller, when we track it by RGB, the DP sensors, using no keyboard or mouse in the way. So we track it, use virtual reality applications, we track it using natural interface. But this track, when we are tracking the body of patient, we have some kind of problem because of the continuous tracking, especially when we use the applications at home, at the patient's home. Because with no therapists in the room, also while the patient is doing the physiotherapy, captures plenty of movement that has nothing to do with the therapy. So postural adjustments, distractions, pauses, the patient stops to speak for some familiar, drink some waters. That's noise for us when we are doing post-stroke rehabilitation database. So as a result, database like Rebase is called Rehabilitation Database, it's an acronym, ends up very noise, mixing genuine physiotherapy with all sorts of spurious gestures. So that's applications is a simple application, a deep learning application, and where we try to keep the clinically meaningful motion, such as compensations and fatigue tremors, while removing the gestures that are not therapeutic. So we want to remove the noise, but we need to maintain the compensations and the fatigue tremors. That is important for us. So how can we remove all the noise? The problem here in research gap, classical filters like Kalman, Butterworth, or B-spline attenuate the high frequency, but they are blind to context. So they can just as easily smooth away a genuine pathological tremor. So that's a problem. You remove the noise, but you also remove the tremor. That's not desirable. Action recognition models such as CNNs, LSTMs, or GCMs take the opposite stance. They assume the input has already been trimmed down to the size of interest. So do not solve the problem for us also. The gaps here sits between the two of them. In continuous uncontrolled strings, there's a kind of noise. Both approach me is semantic noise that we call here semantic noise. Movements that are real but not therapeutic, like resting, drinking water, or shedding. We want to remove all that. So our question here is whether a lightweight model can learn the latent morphology of gait and strip out the irrelevant segments automatically with no per patient manual calibration. So we want to train classification model to identify noise during the physiotherapy exercise. So our proposal contributions here, we propose an automated computationally efficient semantic filter built on multi-layer perceptron. So a simple network, MLP, deliberated not to have a recurrent or graph network, as I said before, because MLP works good for our proposal. It works on knee angles, kinematics over short 5-second window periods. So we track average 5-second window, which keeps it cheap to run irretrievable discriminative. The trick here is to reframe filtering as binary block classification. So each 5-second window we classify as valid, gauge, or noise and rest. So it's 1 or 0. It's a binary classification, a real movement, a desirable movement, or simple noise. In practice, this replaces the manual curation step in the Rebase ecosystem, improving both scalability and storage efficiency. And the results hold up 9.93% of our accuracy and 100% of precision. It's a good result, meaning 0 false positives, generalizing to new patients with no manner pre-showed. A little bit about our MP here. A multi-layer perceptron. I think everybody here knows about that. It's a fit-for network with an input layer, one or more hidden layers, and an output layer. Stacking those hidden layers makes it a deep network. That's kind of the name. Able to learn nonlinear patterns. It learns by backpropagation, as you know. A forward pass produces the prediction, a lossy computed, and then after that, gradients are then sent back through backpropagation to predict the weights of the deep neural network. We use the Adam optimizer for that step here. And for the activations, we use the HELU and the hidden layers, 4 of them, which is efficient and easy to vanish the gradient problem, and a sigmoid at the output to give the binary classification for us. Since rehabilitation data is noise, we also applied linear dropout, an aggressive dropout here. I'm going to talk about that, but we use dropout in some connections between the nodes. A little bit about the data in pre-processing. The input is the time series of the left and right deflection, so only for gauge, stationary gauge that we evaluate here. Taken from the rebase CSV files. We segment the continuous strings in no overlapping 5-second windows, so we split everything. And the ground truth comes from the threshold rule, and per file between 30 and 53 degrees of movement. And our window counts as valid walking when its angular amplitude clears the threshold. We're going to see we have a waveform. And is invalid, that means noise or rest otherwise. At roughly 30 hertz, each window holds 150 samples per knee. Because it's 5-second period multiplied per 30, so we have 150 per knee, but we're measuring 2 knees. So we double that. So we have 300 dimensional features vector. That is our input layer, 300 nodes. We keep the split honest, 6 recording files for training and one completely unseen file for testing, so no data leakage. With the scalar fit to normalize everything, but only in the training data alone to avoid leaking. So we only applied. I only use the training data to calculate the scalar fit. So after we apply to the training, apply to the test. Just a little about of neural network architecture. A deep MMP, as I said, developed using TensorFlow 2 and Keras, taking the input layer with 300 vector. You have here 4 hidden layers. The 2 first here, 128 nodes, and the third and the fourth, the sequence 4 nodes, and the last one, a binary classification, just 1 node with the sigmoid action function. And as I said, an aggressive dropout was taken use, 40% of the first 3 dense layers, then a 20% at the penultimate layer, just to protect the high-level features. That's what we need actually. And a single sigmoid neural then outputs the valid decision. As I said, a simple solution for a problem that we had in our group. Here we have the hyperparameters. Here the network that I just described, the input layer, the 2 reading layers, the large ones, but more 2 reading layers, and the last one. And the validation and the visualization strategy. On the quantitative side, you look at overall accuracy and confusion metrics, keeping a split track of false positives, noise that slips through, we don't want that, and false negatives, gate that gets dropped. We also don't want that, but I think false positives is much worse than the false negatives for us. On the quantitative side, we lay out raw and filter signals grid side by side for each recording file. And for generalization, the model is run on 3 brand new files, M1, M5, and M7. There are different patients, never seen training or cross validation, of course. There is a neat detail here. The final name suffix 48, 36, and 59 degrees encode the manual threshold that each patient would otherwise need, or the gauge. Different patient, different kind of gates. Filtering then without that input shows the model generally learn the latent gauge morphology. So we apply the training model to these 3 patients and try to remove the noise, the semantic noise. We accept the results when the gauge waveforms stay intact, because you have the knee, that's the move that we desire. Here a simple solution we use to visualize everything, because we all have the CSV files with a lot of columns and a lot of numbers, and regarding to to the points of the body. Here we can see what's really happening. Here we can see the waveform. So the skeleton view here lines up the knee angle curves here with 3D motion capture playback button. This is very important for us and for the physiotherapy to see what's happening, not only look to the data, to the numbers. So we really need to use the kind of tool. Further results on the same test set, the 3 patients, the model gets 40, 110 or 404 blocks right, an overall accuracy of 93%. It produces 0 false positive, that's good for us, with 100% of precision. No noise is ever a mistake for exercise, so we remove all the noise in a 5-second window. So the filter behaves like a high security gate for database integrity. So we are using the solution for the database we already have. And now we are trying to use that as a filter in our applications, virtual reality, augmented reality applications. During the data saving, data storage, we are applying, already removing the noise during the storage. The 30 false negatives, a sensitivity of 90% is also good. Reflect the conservative model that puts data purge ahead of recovering everlast gate block. So sometimes you remove some gate, but just part of that. The 4-layer design with its progressive reduction from the first and second layers, 128 to 64, plus the aggressive dropout, capture the non-linear gate features without overfitting. We just have the confusion metrics. The top right cell is 0, is no bad block, is ever predicted as good block, which is what makes the filter safe for clinical use. Here are the results for some training, some models. So training was fast and stable. Accuracy was already past 96% by the TIFF app. So as I said, MLP is a lightweight model and it worked. So that's why we choose them. After 100 episodes, it reached 99% of training accuracy with a residual loss of just 0.0095 residual loss. On the unseen test set settled at 93%, drifting between 93 and 95 over the last 20 epochs. And a small train validation loss gap shows up, which is normal for deep nets, but dropout keep the generalizations steady. And here you have the values that I already mentioned. For the qualitative analysis, we do not use metrics, but we put the whole signal on the left. I will show figures for you. The left sign is with noise. The right side we have with no noise after the filtering. In data 1, along upon a stretch of low amplitude and high frequency signal, the patient stands still and receives instruction. Is removed entirely. This period waiting for the instruction. The shortened x-axis label new index shows the model of discard the unnecessary data with optimized stores. And the waveform integrity is preserved after they remove the noise, the semantic noise. So the high amplitude gate peaks with knee flexion above 60 degrees are kept intact. So you can see here, all these parts here, you can see here, here, and here, we try to remove and bring everything. So as I said, a simple solution, but that really worked for us and remove some noise. And now we are going to test and change training another models and see if it's really impacting accuracy, precision, FU scores. So for generalization test for new patients, the decisive test here is uses 3 unpublished records left out of the training and cross-validation step, the M148, M556, and M759. For the first one, the model cleans up the noisy open moments, suppressing the background noise before motor activity begins without degrading the gate sequence that follows. So that worked great for this patient. For the second one, it handles the intermittence of the exercise. That's good. The patient rests and then resumes, and the model removes the pause clearly. It's okay, it's worked also. While moving average feature would have created artificial ramps if you had used another approach. For the third one, It even spots an acquisition gap near index for 1300, which reinforces that the network internalized the latent gate morphology. It's also maintaining the waveform of the patient of the gate. And all everything was applied with no manual threshold, only use the MLP. Here the generalization test for each one of them. The first patient, the second, the third, and you can see we remove the most part of the noise. Here we have some here, but remove the most part. Remove a great part here. As conclusion, we replace the manual correction of noise pulse stroke kinematic signals with an automated MLP-based semantic filter, preserving the informative cyclic gate segments. So works great for this kind of movement. It reproduces manual correction at 93% accuracy when you compare with a physiotherapist doing the same task, with 0 false positives, and it shrinks the volume of stored data in the process. So we remove the noise, and at the same time, we reduce the storage data. Swapping out manual feature improves both feasible and worthwhile. It's scalable, standardized and time efficient, and it cuts down on subjective bias. In effect, the model acts as semantic editor, remove the semantic noise, keeping only the blocks where kinematic signature of gate is actually present. That is really awesome. This is really what we need for this work. And the broader lesson here is that a simple, well-designed model, given the right pre-processing and regularization, can do a job usually assumed to need much heavier architectures, like CNNs and DNNs. As feature work, as I said, the student who led this work is an undergraduate student. He's still doing his work. Integrate the model directly into the Rebase pipeline. We are doing this right now. So not only filtering the database, but filtering the input of the database during the storage. So the data can be cleaned in real time right at recording. We are expanding the training set to other needle motor pathologies. So not only the gauge, can use the upper body also, and using different sensors, not only media pipe, but such as IMUs, like bands attached to the body. And support data-driven data rehabilitation, where guaranteed information quality is precondition for reliable remote clinical decisions. That's all. Thank you.
Thank you. Questions? I have one about the real-time ability of the model. Can you actually do this that someone is training and the system tells the person that you're not doing it right because it manages to do that this correction of the input data in real time?
We're not doing in real time yet.
Yeah, no.
We're gonna do from now on. Okay. But I didn't get the question.
If it works with real-time systems, or the ability to give immediate feedback to someone who's training.
Okay. We didn't measure that because we are now just worried about the data set, the database. But I think it's quick. It's quick. I think we can use this combined with something like that, and also show to the physiotherapist something like that on real time. That's it. Real time is say 5-10 seconds of delay. Go on.
Yeah, it's a short time.
Yeah, we have a short time. But
and after to give the person feedback that she's not doing it.
yes, but this problem I mentioned before because about the noise, it's because the physiotherapists from the group, they are using the remote but they attend the patients from remote from home, so they don't really need a real time. They're not seeing the patient on the data. So 10 or 15 seconds, it's okay for them. But we do not test this yet.
To be great, because then the person could be doing the exercises and she would know that it's not doing it perfectly.
Yes, you're doing wrong. Yeah, we just stop doing that.
Sort of, yeah.
Try to not create noise for me. It would be better if it didn't, if I don't have noise to
No,
filter. Yeah.
it could be the opposite. It could be not interrupting because the person stopped, for example.
Yes, yes.
It could be the other way, but it's just.
Yeah, it would be great
Make the right
for the patient. Yeah, that's right.
Thank you very much.
Thank you.
So let's move on to the next presentation. So now we have the scaling down hallucination mitigation strategies for compact LLMs. That's 5 hallucinations, which is always a good thing. And we have Saleh still. Oh no, cannot reach. That was my second best option. Thank you. Okay. Hi guys, good afternoon. I'm Renato. First, author Saleh is my graduate student. He concluded your master degree really recently. So the central idea of this work is simple. Small open weight language models are increasingly practical for local deployments. Okay. However, hallucination it's can be correlated for their size. Here we apply on compact LLMs. So the problem, compact LLMs are attractive for local, for private, or considered privately, and at lower cost than larger and bigger models or API systems, based systems. This makes a pyramid of ads, deployments, institutional, and scenarios where data privacy matter. However, make a model easier to deploy does not automatically make it relevant for this. In practice, compact models can still produce confident answers that are factually wrong. Two main problems here is intrinsic hallucination. Here, the model fabricates facts like to, for example, it may input citation or legal precedents, for example, or medical facts or technical details. Second problem is related to is related to manipulation and contracts provided source. LLMs has source documents and produce. The main problem here is a core problem here is compact models are deployable, but they cannot automatically available. And we consider 3 and 4B models, billion models. And factuality and source faithfulness at the two major varies. The research gate here is literature already contains many hallucination mitigation strategies. Nonetheless, much of evidence becomes then larger models, property systems, or isolated experiments. So this work
can more deployment-oriented regime of open, considered open, 3-4 mediums open models, reproduced models, and configuration that are feasible under consumer and edge constraints, like edge feasible configuration. Here is our gap. It's unclear which the gap here is we do not how which mitigation strategies to work when the model is small. A method that works for a 70 billion model or a proper API does not necessarily transfer to a 3B or 4B models, open models. So the main questions is which hallucination mitigation strategies are effective, reproducible, and computational feasible to compact 3 to 4B LLMs. For those by effectiveness, I mean whether the method improves factuality and reasoning accuracy of the model and source effectiveness. But stability of the model, I mean whether method will reduce undesirable generation of behavior, such as task drift, and inconstant outputs of the model under stochastic decoding approach. And by cost, I mean whether the method is realistic for deployment. Some methods improve performance, but only by aiding substantial latency or multiply inference steps. The first step is a systematic review. We identify 216 candidate studies. Then these candidates exploring according reproduction and feasibility. The goal is just comparative between them, and the story will go up. The studies was between 2021, 2025 screen window. This produced 8 representative mitigation configurations, and with configuration, they were evaluated across reasoning, factuality, and summarizing benchmarks. And ferret bootstrap analysis we consider to estimate whether observer difference were meaningful at the instance level. We consider a mitigation taxonomy. Taxonomy organized the fragmented hallucination mitigation literature into 4 practical strategies. The first strategy is model optimization. This method modifies the model parameters through fine-tuning. We consider fine-tuning. And related training time strategy. Second family is inference. These methods do not model weight of LLMs. Instead, they alter the decoding process or logic during generation of the model. And the third family is external knowledge. These methods use retrieval or source provider evidence. And the fourth category. These methods, latent intervention. These methods considering aim to exchange the model behavior without parameters, weights, updates. Configuration, we consider the Quen model, 3 to 4 billion of parameters. The evaluation configuration were Shadow FT, DOLA, and Replut, and Gaussian steering. These represent the 4 mitigation categories, considering the first optimization, decoding control, DOLA, and retrieval-based stabilization and activation steering. And the baseline for Llama 3. The evaluation configuration were HERD3, PAT, NAIF, and iterative REG and IT PAT. The important point is that this is configuration level comparison. Okay, it's not method to method comparison. The claim is not one category in universally better. The claim is that under the compact model, those compact model configuration, methods behave different depending on model and the task applied to this model. So evaluation test for reasoning evaluation. The benchmark use ARC challenge, ARC easy, and the OAB legal exam dataset is exam considering lawyers like to bar in USA, bar exam in USA, in Brazilian order of lawyers. This gives both scientific reason and Portuguese legal domain, OAB, evaluation. For generative factuality, we consider proof QA and NP open. Proof QA test resistance to common face, like to face holds, and NP open domain captions answered in LLM domains. Fairfulness, we consider use CNN Daily Mail dataset for summarization with Roach and BERT4 and Drifty reads. These metrics capture the both lexical and semantic alignments, plus whether if the model stay on tasks originally. Here, the deterministic tasks were run once, and while generative tasks used 5 independent runs to account for stochastic decoding variance and extract the statistical metrics. This table shows the best method depends strongly on the task considered. For grain 3, Replut gives the clearest improvements on OAB, going from 0.2 to 0.4. And that suggests that retrieval is especially useful when the task depends on externally. Externally with recoverable and domains knowledge. For Quen 3, Gaussian steering, considering the best ARC challenge results that suggest activation of history. On OAB, HERMS3 perform best of llama, which suggests the supervised fine tuning is transferred to Portuguese legal status. The main message here is that reasoning on domain knowledge are not the same problem. And retrieval helps most clearly when the missing information, and while reasoning can benefit more from decoding and heuristic methods. In relation to generative factuality, when 3 is already strong to QA. For llama, the patterns is much more dramatic. The behavior truth QA score is low. For llama, the strongest factuality gains come from internal align. And any key open. Retrieval is not automatically beneficial if the method context is noise. When retrieval hurts, the key lesson is that retrieval is not always grounding. Adding context does not guarantee that the model will use the right context. Here is the findings. So observe the facts. Here is the replug worsened Quen 3 performance on NQ open. The same pattern appears for Navy rack and llama 3.2. Likely mechanism used in the error analysis. The main failure models were entity contamination in this context, position bias of the model, and incomplete evidence. Entity containment happens when the model copies a solid but wrong form of retrieval text. Position bias happens when the model overhits the entity, and incomplete evidence happens when the retrieval phase is relevant but missing the crucial details related to outputs. For complex models, this can be especially harmful because the model may over the retrieval is night. So retrieval can turn from evidence in distraction that explain the naive rack can help truth QA, but hurts NG over.
We need to move towards the end.
The end, okay, is the source performance and the replug source and IT strongest and codes and the main takeaway. The single bit cage method dominates across all tasks. When in a related environment, llama and alignment and steering. Retrieval is powerful, considering introduction, distraction, and compact LLMs requires configuration level and not method to method evaluation. Special thanks to UFMS for that, and thank you.
Thank you, Matt. So, quick questions. One.
Just a quick.
Okay.
How you know before besides that, what's hallucination on a model to test to evaluate which is that hallucination as popular called hallucination?
Oh, yes. Yeah, we consider the output of the text output. And for a previously test, with text, we consider in the output. Is a trusty way, is a benchmark to evaluate it. Here, for reasoning, for factuality, is a trusty way.
Okay. Thank you very much.
Okay.
Very well, let's move to the next speaker. So now we have Dario Shibaimi for an integrated congestion aware framework for task allocation and path planning in a multi-agent pickup and delivery.
Sorry. Sure.
Presented most has to be. Sim, sim, mas a pessoa que recebeu essa botão do presente tem que mudar alguém. Qual são os chamados? Agora já em novo, estão sem projeto, vamos apresentar esse
Parece que
Parece aí, né?
desaparece. Não vai ficar aí. Eu já fui aplicar para ver os dois. Podes mudar aqui.
So, tell us about your work.
So this is a PDF, right?
Yes.
Just kind of try with the PowerPoint and then
Okay.
you can use the PDF and
Sorry,
save it
that's
in the
it.
Word. Let me see here. So what you post this one,
Doesn't like
what's gonna happen?
Here it works, but
Yeah, that's fine.
okay.
So,
Okay.
Step right
Okay.
last time.
Online.
it's visible.
Mas não vai para
Here?
No? Here is what.
Alguém a mais? É para se mudar. Okay.
Okay, thank you so much, Mr. Chair. My name is Darish Ibrahimi. I'm from Wilfrid Laurier University, Department of Computer Science and Physics from Waterloo, Ontario, Canada. And I'm here to present the work of my graduate students in one of the courses, actually. This is a project work for a group of my students in the course. And I'm here to present their work which, with the title of an integrated congestion-aware framework for task allocation and path planning in multi-agent pickup and delivery. Very long title, I know that. But I see there is some odd here. I'm the only one from Canada, and all the presenters here are from Brazil. So consider me as a Brazilian. My name is Ronaldinho. Okay. So first thing we have to know, what is the problem? And I believe that by looking at the picture, you already guessed what is the problem. So here we have a warehouse with a lot of robots, as you see in the picture. And the task here is that, or the objective here is that we wanna give, we let all the robots to pick up items or boxes, as you see in the figure, and deliver it to the delivery point. So this is going to be the task, but the problem is we want to let all the robots, which we have thousands of robots, to do the work or do the task here without colliding with each other or creating a congestion in the warehouse. Because if there is a congestion there, we're going to slow down, and our objective is to fasten the delivery of the packages. So consider this warehouse as an Amazon, as an example, that we need to deliver packets from a source to a destination. But it doesn't look like very simple, this problem, because actually we have three main challenges. So the first challenge is, for sure, is the scale. So here in this warehouse, we have thousands of robots. We don't have one or two or three or few robots that's going to be very easy to manage, but we have a lot of robots here, more than 3,000 robots in this warehouse. So managing them, assigning tasks to the robots, it's not going to be easy. So scale is one of the problems that we have. The other problem is the real-time decision. So we have to make a decision right away because the tasks are coming one after each other. So we have multiple tasks coming to the warehouse that we have to assign the task to the robots to work. Not okay, it's not showing. Yeah, real time. I don't know how it's disappeared. And the third challenge is the congestion, or if we give multiple tasks and we make a very fast decision, then there is a high chance of having collision or having a traffic jam among the robots while they are delivering. So these are the challenges, but the solution is to develop a smart system which controls the robots and assigning tasks to robots. Now here what we have to consider for our smart solution here is to assign tasks to a proper robots here, because robots are distributed in the warehouse. So we have to know which task or which box should be given to which robot. Maybe you can say that, okay, the closest one, we give the task to the robot and then gonna deliver the basket. So we know the robot is close to the box, we assign it to that robot, but regarding the destination is something else. So we have to worry also about the path planning. So we have to do a good path planning in a way that we consider the traffic in the warehouse as well. And last not least, we have to resolve the conflict if it happened on the spot. That means instead of sending all the conflicts or the problem, if there is any congestion or traffic in the warehouse, to send it to the central unit to replan from the beginning, it's going to take time. So we are not going to go with the real-time decision here. Hence, we have to solve it locally at that part where we have a congestion or some traffic. In this way, we're going to fasten the procedure. So the key insight here is that, I don't know why this one is showing, but anyway, the key insight is that we have to think or plan and think about any congestion that might happen in the future. No need to be a very long future, very close future, going to be fine. So we have to predict the congestion before happening. And based on that, we do the planning and also we make a task assignment. A lot of details in one slide. So we got our key insight. So let's go home. My time is over, I believe. No, that's not yet. We are not yet done. Let's continue to talk about the problem and about the solution. That was the key insight that we have to think about when we want to create or build a smart system for this problem. Now, the problem in the literature called multi-agent pickup and delivery, in short, MAP. There are a lot of studies in the literature talking about this problem, by the way. So what is this problem in the first place? I already explained this one. And in very short explanation, this problem that's being studied a lot in the literature is nothing but coordinating multiple robots to pick up and deliver items by avoiding collision to fasten the delivery or fasten all the tasks that we have. And it is proven in the literature, it is an empty heart problem. So it is not an easy job here that we are doing. It is very complicated. Okay, so we said that it's already been studied a lot in the literature. So what is new here in our world, or what my students, they already done? Actually, they got their grades based on their project and they passed. If there is no novelty in their work, so they should fail. But let's continue and see what the student already done here. First of all, we have to talk about the system model that we have. We model the environment of the warehouse with the robots as a graph. So in a graph, as all of you know, we have set of vertices where they are the robots, where we have 1,000 of robots here, which we consider as a vertex in our map, and also regarding the edges, so it's going to be the path or going to be the steps that the robots will take as the edges. And I will talk about the map itself in a second. And the task going to be just pick up and deliver through the assigned path. Now, we just briefly put all the methods that been discussed for this problem from the literature. So we have different methods and their approaches and the limitation. Each method has its own limitation. So what is the gap here? We found that there is no any approach that considers or combine the following. So we have 4 components that we have to take care of in order to have a very smart and very efficient and good method. So the first one is congestion-aware task allocation. So whenever we want to assign any task, we have to think about if there is any congestion in the future, or when we assign a task to this robot, there's going to be a congestion or not. And also we have to be careful regarding the path planning. So it should be an efficient path planning. It is not as easy as we say that, okay, let's go with the shortest path. No, if we take shortest path for all the robots from the source to destination, there's going to be a lot of congestion, and it will slow down if we have a congestion or conflict between the robots. Then also we have a scalable conflict resolution. So if there is a conflict, because we don't know, we are thinking very fast, we are planning very fast, we are assigning tasks very fast, but if we have a conflict, so then we have to think about refining the path in order to avoid the conflict or congestion. So we have to do it very fast, and we should have a refinement plan while we are managing all the tasks and also the movement of the robots. And the last not least, we should have a real-time execution. That's the most important thing regarding any solution that we want to think of or build. So it should be fast enough. Now, in this research work, the time given for the method or the solution is within 1 second. Actually, it should be within milliseconds, but not more than 1 second. So it is the limit that we put. 1 second, we should have an answer. So the innovation or the novelty of this work is we integrated all these components here, the 4 components, and we don't do it in isolated parts. So all should be done in one algorithm, or not in one algorithm. All should be done combining or integrated all together. So let's talk about the solution itself, how we integrated all the parts that we just discussed here. So the first thing that we have to know is the components of our solution or method in order to integrate all the components mentioned just now. The first thing is task allocation. Now you see here we named it algorithm 3, but there is a reason for that. So it is a task allocation. In task allocation, we have to think about the congestion awareness, or if the congestion going to happen if we assign a task to a robot. So we have to think about that as well. And this is nothing but a greedy-based heuristic or algorithm. Then we have the next step where, because for this one, we need to be aware of the congestion that's going to happen, because congestion happens if we plan a path. So here we have another algorithm that tells us or plan for us the path that the robot should take. So here, for this algorithm, we use the well-known A-star search algorithm, but we modified this algorithm a little bit, which we added a congestion penalties. We will talk about the congestion penalties in a moment, but this shows the step. That mean first, for the task allocation, we need first to think about the planning, and then we're going to assign the task for a robot. So we are not going to assign a task right away. We have to plan a path, and then we're going to, if the plan is good, then we're going to assign a task to the robot. So here we have to do it in a dynamic fashion, where even the path, although we already planned it, but maybe in the future, because everything changes, the traffic flow change, and more tasks comes in, more robots will do the job. So sometimes we need to replan the path of robot or robots. Now, in order to do the congestion, in order to understand the congestion and the traffic flow here for the path planning, we need a third algorithm, which called a priority-based conflict resolution. Actually, this is taken from the literature. This is not from us. And we saw that this is a very nice and good algorithm in order to solve any conflicts that happens between the path of robots. So we borrow this one from the literature, and the good thing about this one is that it's solved the conflict, and it has a very good advantage where it does the backtracking. And the backtracking happens if this algorithm, when there is a conflict, and instead of detouring, sometimes if the detouring of the robot will not work, then a robot will step back one step in order to give a room for the other robots to move on to resolve any conflicts happens. Now, if you look at this, these three algorithms that we do it, that they need each other and they are integrated. We talked about the first, second, and third, but we named it algorithm 3. Here we have algorithm 2, and then we have the method or algorithm from the literature. But the right way of solving such problem is to going backward from 3 to 2 to 1, because as I explained, for 1 to be solved, we need 2, and for 2 to solve the 2, we need number 3. So it goes in a backward direction. This is why we have algorithm 1, then this 2, then algorithm 3. But when we want to explain it, for sure, we have to go from task allocation when we want to implement it, task allocation, then path planning, and then solving. So the framework looks like this. First, we have to do we have a prepare stage, then we have a plan stage, then we have the results, and eventually we have a refine stage when we have a conflict. So all these stages that you see should be done on a fly. So we have to do all of them together as an integrated algorithm or solution. Now let's talk about task allocation and path planning. I will go very fast over here because I do not have that much time. So regarding the task allocation, to discuss it very briefly, how we assign tasks to robots or agents. First of all, we have to see what are the tasks that we have and what are the robots that are ready and there is no any task assigned to them. So we're gonna take them and then we gonna put some cost on the path that they have to do regarding the task that we want to assign to the different robots, and then we pick the one with the minimum cost, or let's say minimum penalty. And regarding the penalty, which is the penalty depends on the congestion that we're gonna get. So here is how we assign the penalty, and for that we use, as I explained earlier, using the modified A-star search. So if we have an opposite path between two robots, then we're gonna give a very high penalty for that. If we have a conflict, but both robots are taking the same direction, we give something like medium penalty. And if there is no any conflict or the path will go through a very low traffic, then we don't give any penalty. And based on that, we assign the path that gets a very low penalty. So we sort the task along with the robots. We sort it, and then we give the minimum to the robot, the task to the robot. Now, if you want to talk about the method that we borrow from the literature, which is the priority inheritance with backtracking, in other words, PIBT. So here, this method does the refinement in a dynamic way. In this decentralized way. That's why we can have a local refinement in our solution instead of sending the problem to the central unit to solve it along with the 3,000 or thousands of robots at once. So we will do it in locally because this method works in a decentralized way. So the method is very simple. The robot that has a higher priority we can assign the priority, and it has some statistics, but let's avoid talking about that one, but you can define yourself what's going to be the priority. So the higher priority agent will block the lower priority agent in this way. So it means that if I have a low priority and there is a high priority agent or robot is coming in, then I have to give the path to the high priority agent. Now the backtracking happens in case if I cannot give a path to the high priority agent, so I have to go back in order to give a room for the high priority agent. Now you are wondering, why do we need to step back? So if we don't go to the front and we give a room to the agent, but the problem is, depends on the map, because sometimes, let me show you an example here. We have a very narrow corridor where here there is a path only for one agent. And if there is another agent coming from the front, or let's say from the front, because this one going in that direction, then where is it? Then we have to step back in order to give a room for the higher priority agent to pass through. That's what we have to do. Now, regarding where I am, so backtracking, I'm not going to explain it. Now, why deviation occurs? For many reasons. One of the reasons is because we have a limited planning time. If you remember, we have to decide, do the task assigning and as well as path planning very fast, within 1 second. That's our limited time that we have. So sometimes randomly, we will assign tasks to agent. So that's why, because of limited planning time, we might need to have a deviation for the path of the robots. And also, based on the PIBT method, sometimes we need to do detours, and also some of the higher priority needs room, so we need to change or replan for the path. Now, regarding the refinement steps, this is a step, so you can read the paper. So I will go through. Now we reach to the part where we need to evaluate the performance of our methods. Now here is the experimental setup. Now I'm not gonna talk about the experimental setup here because of the time limitation, but what's important is that this is our map. The map is that we did the evaluation 140 by 500. Now, as you see, there is no unit in front of it. That's because for our map, in order to give a task and then plan for the path for the robots, for simplicity, what we did is we said that we're going to work on the movement of a robots step by step, like a human. So I will take one step. So it is one cell. Then the second step, this is another cell. So these are the cells. So we map it as a cells. So the robots, they know if we give a number, so go from cell 1 to cell 2, or this cell number to this number, so we know the path that the robots should take. And for sure, we have a timing because we have to do schedule, when to move one step ahead, when to stop, at which time slot should move. So it is very important. Now, if you multiply, you will get 70,000 cells here as a map. And we put between 250 to 3,500 agents or robots in this area, which is a small area. Now, regarding the corridors and the blocks or the rows, as you see here, or shelves, we made our, let's say, a map for the corridors and the boxes and location of the boxes. So it is a design environment here. So let's move on. Now, what we measure, so here are all that we measure, the number of completed tasks, very important to see, within a time frame, where the time frame here is 2,500 time steps. As I say, the number of cells. So this is, or the time steps for our evaluation. We start at the time step 1, then we finish our evaluation at 2,500 and see how many tasks that we have completed. And then we should check the number of idle agents. Not all the 3,000 or 1,000 agents they operate, because if we let all of them operate at once, there's going to be a lot of congestion and we slow down the task. So it's very important to check how many agents are idle, not giving any task. Now let's continue to the result. I will just tell you about the key findings about the results, comparing between the best method from the literature with our method here. So let's not talk about the result from here, just the key findings. The key findings are our method gives more than 38% throughput. What is the throughput? The number of tasks that being completed here. This is for the result for when we have 3,000 agents. And also our method shows that it's we have less than 30% of idle agent compared to the other method, and we have a stable completion time. I need to explain about this one, but let me go on. Why it works? Because of these reasons. Integration prevents bottleneck because we integrated all the 4 components, and the local decision avoids central control because we have a local decision instead of sending it to the central unit. And the congestion awareness are all adjusted. We are predicting the congestion in the future or calculating the congestion and avoiding planning the path or assigning tasks if there is a congestion. And then last not least, we have a deviation handling keeps agent on track. So we have a refinement age where it works. So successfully we did the experiment for 3,000. In the conclusion, first thing that we have is the method that we come up with is scalable and robust, and it gives a result in a real time, good result in a real time. As a future work, so we have to work on the different maps for sure, different maps. And also we need to work on adaptive task generation, the incoming rate of the task, and last one is to predictive, we have to do the predictive allocation. So that's all. Thank you so much. Sorry for taking time, but we are done with this conclusion. Thank you so much.
Any pressing question?
Yes, I do have actually many questions, but I think the time constraints. I find this topic very interesting. I am particularly interested in reading about the ASTAR modification movement, because this type of algorithms are much greater valuable these days.
Yeah.
And so I suppose you don't have a paper about this algorithm itself, because it was developed by your group, right?
Yeah.
Yeah. I'm very interested in that algorithm, but I will look for it. But my real question is this: I think that this problem is actually present in many solutions, including in Google Maps.
Mm-hmm.
Because Google Maps is actually rerouting us, and it seems to me that it is not caring about the dynamic aspect. You told that when you redirect robots, it will influence the congestion or already present congestion. And so, if you research a scalable solution, this can be applied to another problems.
Yeah, sure. Even this is very close to traffic management, as you mentioned, regarding the Google Map. But the big difference between the Google Map and any routing, let's talk about the vehicle routing, not robots. The main difference is that in Google Map, just sees the picture, the traffic flow, and then will tell you it's better that you take this path. So it will give the same to all vehicles.
Yeah.
But this one predicts the path and sees whether there's going to be congestion in the future or not. Google Maps doesn't do that. That's the main difference.
I have many questions. Maybe you can talk later. I have to leave now.
Okay.
But congratulations.
Thank you so much. See you in the coming gathering at night.
Yes.
I think you will be there. So nice talking to you.
Thank you very much.
Thank you. Thank you so much.
Okay, so moving to the next presentation, the last one. We have Caio Guimarães. Okay.
Thank you. Hello, everyone. Thank you for staying. I will try my best not to hijack the whole coffee break time. So I'm here to present the paper called Detecting Real Software Faults Through Resource Consumption Anomalies, an evaluation of the recorder methodology. So just to give some context and motivation, we are talking here about a solution that flows in the area of software reliability. We have traditional software testing as an expensive and time-consuming activity. We have more and more complex systems that are presenting failures in production environments, even though they go through like a bunch of regular testing when they're in development. There are multiple non-deterministic aspects of production environments that might influence in that. And the field of reliability engineering is trying to compensate for this and trying to aggregate more techniques to ensure software quality in those types of environments. One of those techniques is regarding the monitoring of resource consumption that can indeed indicate the existence of faults. So in this context, there is a methodology that we developed a few years back. We call it Recorder. This is not a contribution for this paper. The Recorder methodology has been studied for a while now. And to give a very quick, very brief overview on how it works, we have a monitoring script and analysis script. The idea for the monitoring script is that we have an environment where the application under test, the system under test is running, and a regular scenario, regular expected run. We do have a set of workloads that are used to basically qualify different behaviors for that particular system. And we are not looking at output data here, but we are looking at how does that system consume the resources that it has, like RAM, CPU, and other types of resources. So this monitoring step is basically collecting some metrics and generating what we call profiles from how a particular execution goes. Then we have an analysis step, which is responsible for grouping those profiles with an unsupervised grouping algorithm. And the result of this process is those profiles being grouped together, where each group kind of represents a particular behavior for that application under test. So the first iteration for this methodology, we call a reference version of the application, which is basically a stable version, a version that we don't know any defects. And then what we can use is to test a new version of that application, what we are calling here anomalous, assuming that there is already an anomaly. But overall, it's just a new version of that application that will be compared to the reference one. And the idea is that if there's any anomaly in behavior, it's expected that here we'll have a new group being formed, which contains only profiles collected from this new version. So this could indeed indicate an anomaly, indicate a defect in the software. It could also be just a new feature that was added, a new improvement in performance. So this needs to be evaluated by a tester or someone who has some knowledge and context on what has changed. So this is a very quick overview. As I mentioned, this has been studied before. We have multiple works here that explore how does the recorder methodology behave in different contexts, in different application domains. The only issue here, the thing that I want to highlight, is that despite having good results, they all work with artificially inserted defects. So all the applications that were tested, they were manipulated and added some defects to create new versions. and those versions, we were able to capture those defects, but they were, as I mentioned, artificially inserted. So our next step here is to try and leave this artificial scenario, leave the experimental phase of the tricorder methodology. One of the ways that we're trying to achieve that is by encapsulating that methodology in a tool, a reliability tool that we're calling Triad, tricorder-based anomaly detection. There is another paper in the oven about to be published that basically covers the technical aspects of this tool, so I won't be discussing that here. But we are starting to use that tool to conduct new experiments. And the experiment that I'm about to discuss here runs around the defects4j dataset. So this is a kind of a well-known dataset in the software engineering context, not necessarily here. So just to give a brief overview, defects4j is a dataset that contains multiple open source Java applications and different versions of their code, including bugs, classified and labeled bugs, their fixes, pull request messages, and a lot of information that we can rely on to test on actually real existing defects, including tests that capture those defects. This will be important in the future. There's a classification from Spy and Fisher that look at those defects from the defects4j dataset and classify them in 8 different types. Some of them are control flows, some of them are data flow defects. And within the overall set of defects in defects4j, we selected defects from 7 different applications covering the 8 different defect types. The experimental setup was basically, we generated a combination, we generated 10 executions for each combination of application type and defect type. For each execution, we generated 30 profiles. Basically, we are saying that we are running the application 30 times. And keep that number in mind because this represents that at the analysis step, we can have up to 30 iterations of the grouping because we're going through 30 profiles. So we basically evaluated whether Triad was capable of distinguish between defective versions or regular versions through the number of iterations it took for it to detect a new group. Experiment was conducted in a virtual machine. And overall, we achieved a 33% anomaly detection rate with no significant distinction between applications or defect types. We were kind of expecting to see some specific patterns here, but we didn't. But if you recall from the brief related work slide that I showed, this is a very low number in comparison to the previous experiments. This is somewhat expected because, as I mentioned, we were heavily influencing the ability of the tricorder methodology to find those defects due to their being artificially inserted. And right here in defects4j, there was no filter for high impact or low impact in performance. We have some defects here that are just a single line change, changing how a date time is presented, like the format of the string. So they might not necessarily be that impactful. But still, even though this is a low number for our standards, optimistically, it could say that at least a third of the defects on the data set could have been caught before going to a production environment. If, for instance, Triad was set up in a CI/CD environment or something similar to this. When we look at control group execution, those executions that the application version did not have at least a known defect, we have a 71% of correctness rate overall, so the average. When looking at the actual number of iterations that it took for the tool to detect a particular defect, when we look at the existence of defects, we're talking about an average of 26.5 iterations. And when we look at the control group runs, the average is 27.3. Here, basically what we want is that this number gets as close as possible to 30, because if we go to 30 iterations without detecting a defect. Basically means that that particular run did not flag anything as a defect. And here we're talking about control group. So that was the expected behavior. Although the numbers for iterations are kind of similar when we look at statistical analysis running the one-tailed Wilcoxon signed rank, we could see that there's significant evidence on the distinction for these values and the values from the previous table, which can help us say that the triad is able to differentiate between a normal run and a defective run. As I mentioned, the score that we got for detecting defects is kind of low. The F1 score overall is 39.18%. We still have room for improvements, but as a reminder, this is the first time that we're looking at real defects, and we are not filtering anything that is, in fact, necessarily impactful in terms of performance. So we look at this with very optimistic and very exciting glance to say. Moreover, there is indeed a threat to validity of this experiment. This is something that we need to work in the future works, which is even though we are looking at real defects, we are looking at them through the lens of the tests that capture them, not necessarily an actual run for that particular tool that hits that particular defect. So this is basically a layer of abstraction that we have from a real scenario. It's closer to a real scenario than what we had before, but still there is a layer that we need to surpass. In conclusion, within this setup, Triad were able to detect real defects using the defects4j dataset with a fault detection rate of 33%, while maintaining a correctness rate of 71%. This approach still requires improvement, has a lot of room for improvement, but there is a statistically significant distinction between defective runs and regular runs. While there are opportunities to improve, there's also potential for both third quarter and now Triads to support the detection of real defect. As I mentioned, if we are being extremely optimistic here, we could say that a third of those defects could have been caught before reaching production environments. And future work basically needs to address the threats to validity that I mentioned. Hopefully, we could apply Triads in an end-to-end application development environment instead of relying on source code that is already built and already, like the bugs were already fixed. So we're looking at the past now. We want to look at the future, basically.
Great. Thank you very much. So, yeah, maybe last question before we go.
So, small question.
Yeah.
For the presentation, I didn't get if it's a limitation of the recorder or is it more related to the data set. But we probably better
the threat. Yeah. Okay. So on previous experiments, what we did was to actually run the application. We could set some input values for it, but the application runs as expected. Like it will do what it needs to do. When adapting to defects4j, we kind of lose the ability to run the application. We can run the tests, and we are certain that the tests contained in the data set, they capture the defect. So we can look at a scenario where the defect is running and where it's fixed. So we have the ability to compare those two, but we are not actually running the application and hitting that defect in the actual. So that's the limitation.
Okay, very well. Let's thank again all the speakers. Here is the next session.
I was just wondering,
A gente pode deixar as coisas aqui, eu posso perguntar na próxima sessão,
Esse, meio foda, eu não vou fechar as portas. Eu sei, mas vão voltar a fazer mudanças.
Bom, vou deixar.
Eu encosto de fora.
Beleza, obrigado.
Nada.
Bye.
Esta sala realmente está quente.
That's not bem.
Sim, quando estamos cá dentro, o primeiro acho que é o mesmo. Este.
Olá. Aqui vocês também falam, os últimos serão os primeiros?
Tem não sei se pus aqui.
Sim, também se usa assim.
Não.
Não, eu não tenho pendrive, mas eu posso mandar para um e-mail.
Deixa eu ver.
Se quiser, eu abro meu e-mail. Não tem
Se
problema.
calhar é mais fácil.
Ok.
Acho que se calhar é mais fácil. É o único que é presencial, não é?
Único presencial.
Vamos todos para a online.
Não quero apresentar aqui ninguém.
Só minha namorada vai chegar aqui.
Já temos então.
Ainda tem alguma. Isso é bom, não sei.
Assistência C4.
Oh, perdão.
Não faz perguntas difíceis.
Perdão por tudo, tá? Desculpa pelo atraso.
Não faz mal. É melhor. Vai ser melhor.
Temos som da sala. Temos som da sala, as pessoas falarem. Ouve-se, não é?
Sim, basta falarmos assim. Geral que eu venho.
Okay, so everyone online. So this is the session. So this is the session 9B, general track.
We have 5 speakers. We're about to begin. The first speaker is already here in the room. Can the other speakers say they are present? If they are, please.
Hello, the last one, Sergio.
Is there any speaker present in this virtual room?
Yeah. I'm Sergio Freitas, the last speaker of the section.
Is one of them?
At least trying to speak.
Okay.
Hello, Sergio.
Yeah, hello.
We can't hear you, but I suppose that's not. It will not.
Are you
be
hear me?
at some point. Hope.
I think this is on us because the blue thing is showing there.
So Sergio is the last one, okay?
I'm the last one. Thank
And
you
then
very much.
Hi, I am the second one, Korhan.
Okay, so then we have. I can see the names. Coran. Okay, is the second one.
Yeah.
And we're missing the others. But at least we have the 2 first ones, so let's hope. Hi. So we still can't hear you. Okay, that's. Are you trying to speak? Can you just try to speak so we can be sure that we can hear you? Any of you?
Hello, Sergio here. Are you hear me? Oh, there is echoing.
All right.
Sorry.
Is that from your side? Não tem microfone. Não, tem microfone. Microfone não. Mas não depois me ouvem.
Ligar o
Eu preciso ter este ligado para.
Quer falar sobre
Não,
essa?
ok.
Mas se quiser.
Esperamos que eles ouçam por aí. Okay, so we are moving to the first presentation by Caio Guimarães Herrera, and then we'll hope that for the other ones, for the virtual ones, it goes smoothly. Okay?
Okay.
Please.
All right. Hello, everyone. Thank you for the in-person invitees and the virtual ones. I see some familiar faces from the previous session, so just bear with me. The first slides will be similar to what we discussed, but we are here to talk about an empirical study of compression strategies for tricorder, from general purpose compressors to the channel engine. All right, so just to give some context and motivation for this, we are talking about work that is located under the software reliability area. We have traditional software testing as an expensive and time-consuming activity. It requires previously some knowledge about the software that is being developed. We have non-deterministic aspects of multiple production environments that might cause some faults in complex systems that are not necessarily able to detect those faults with traditional testing during development. So we have the reliability engineering area coming here with a new set of tools to try and help with assuring quality for those systems that are being developed. One of those tools is the ability to monitor the resource consumption usage by a particular system and use that as an indication of a possible existing fault. So we have the tricorder methodology. This is a work that we've been doing for a few years now. This is not a contribution for this paper itself. This is something that we're leveraging and trying to improve. So this methodology, just in a few words, how does it work? We have a monitoring step and an analysis step. And the idea is that we can set an application to be executed in a particular environment, and we'll be monitoring how does that application behave in terms of resource consumption. So we can look at the usage of RAM, we can look at the usage of CPU and all the other aspects that we can get access to. And by collecting those, we can define a set of profiles that represent how does that application behave. So those profiles are sent to an analysis script, which is responsible for grouping them and trying to define different behaviors, different expected behaviors for a particular application. So we have a first iteration of this process, which is done with what we call a reference version of that application, an initial version that we consider to be stable and preferably with no known defects. Then we can run this process again with a new version of the application. Here we're calling an anomalous version, but this could be just a regular version that is being deployed now and that we want to validate. The idea is that we'll submit that version to the same environments, to the same executions. We'll collect the profiles, we'll generate we'll collect the resource consumption data, we'll generate some profiles, and then we'll group those profiles in a similar group to what we had before. The idea is that if a new group is formed with profiles generated only for this new version, it means that we have a new type of behavior for that particular application. And this could be an indication of defects. This could either be a regular change in the application, like a new feature that was developed, or performance improved that was done by the developers. So we still require some tester or someone who has knowledge on how the application behaves and what were the changes, but this can be an indicator of a possible fault being added to the code. Now, for this work, we're looking specifically at the analysis step, where we have a second methodology being used. This methodology is called DummyCore. It's also a product of some previous researches. And basically, its goal is to group unsupervised, do some unsupervised grouping for generic data. So in our case, you can see that we have binary files that we call profiles, and those profiles are being grouped with one another. This methodology consists on three main steps. First one, it computes a distance matrix for each pair of inputs, each pair of files. This matrix is transformed into a phylogenetic tree, and this tree is grouped, and from that particular tree, we generate the groups based on a hierarchical clustering. Since the inputs on our case are binary profiles, as I mentioned, one of the distance metrics that we can use and that was selected for dummy core is the normalized compression distance, where we compress the files and we basically compare the size of them. So we have the exact formula here. So we're considering files X and Y. If we apply the NCD between those two, we're looking at a compression function, and we are comparing the size of the compressed concatenation of those files with the minimum and maximum size of each individual compression. It's expected that we have a metric value here between 0 and 1, while if we go closer to 1, we have a more distant pair of inputs, where if we get closer to 0, we have more close inputs. This is indeed the most time-consuming step in the dummy core process, and it's also very critical for Tricorder's results, as its performance heavily relies on the quality of the compression. Therefore, the choice of compressor that we use really matters for the performance of the overall testing activity. We had some previous works looking at some of the more general purpose compressors like zlib, gzip, and ppmd. These are lossless general purpose compressors, but for this study, we wanted to look at other compression strategies. So we are also including multimedia compressors here, both lossless and lossy. And as I mentioned, we are dealing here with generic binary data, not necessarily images or videos or anything that is multimedia. So we indeed, to use those, we are also requiring some pre-processing steps to convert our input into a desired input for those. Also, we don't have necessarily a global optimal solution for this compression problem, as performance is kind of dictated by a trade-off between the compression rate, how small can we make those files, versus the response time that we take for compression. However, NCD is a practical approximation of Kolmogorov complexity, which describes the information contained in an object by the smallest size that we can get for an algorithm that describes that particular object. So when we look at the literature, we can see that there's an equivalence relationship between this Kolmogorov complexity and Shannon entropy, which can be used as an approximation of the resulting size of compression in an ideal compression scenario, without requiring us to actually compress the file, which can theoretically accelerate this process. So back to that list of compression strategies, we are also adding an entropy computation here based on Shannon entropy to try and get a new angle on this, a new perspective on this challenge. Okay, so for experimental studies, we did a virtual WSL environment running Ubuntu, previously known application lab application. This is just a educational application that compiles different decision tree algorithms just for us to be able to explore the Tricorder methodology in this context with different compressors. If you were in the previous session, I mentioned some related works that worked with artificially inserted defects. This is one of them. So we have a set of 7 defective versions and a control version with no known defects. And here we have just a summary. We have 3 types of defects with low impact on performance, 2 types of defects with medium impact, and 2 types with high impact. Additionally, we have the control version, which is expected to have no defects. We ran each combination of compressor and version 30 times. And for those, we evaluated both effectiveness and efficiency. Effectiveness as the median number of iterations needed to detect the defect, while also considering the false positive scenario. And for efficiency, the median response time for an anomaly to be detected. Or if that anomaly is not detected, we take the total time that it took for the Tricorder to run. We will also consider the median iteration time to see what is the impact of the compressor choice in each iteration of the analysis step. For the preprocessing that I mentioned, the strategy for multimedia compressors, basically we wanted not to apply any transformation on the original data. So basically every 3 sequential bytes we consider as a single byte of color. So kind of close to a bitmap file. So going to results, this table shows the median number of iterations for each compressor. We are signalizing here the impact of each defect type according to its the impact and performance. So we have low impact here, medium impact, and high impact. Here we have the different compression strategies, the control group where we are not supposed to find any anomalies, and just to reference the median of each column where green cells are below or equal to the median. So at first we don't see, we don't see a big patterning standing out here, but we can see that most of the multimedia compressors are seeing false positives, with the exception of PNG. And we can also see that the median number of iterations that it took for an anomaly to be detected somewhat correlates to the impact that those defects have. So you have low impact on performance taking longer to be detected, while high impact performance takes less iterations to be detected. Now, when we look at the median response time, a pattern starts to show up. So we see that the generic compressors tend to take less time to detect the anomalies. Additionally, we have entropy performing good as well. This is correlated to the fact that we don't have to actually compress the file. So it is expected that it would have a good performance here as well. For the multimedia compressors, we also have the preprocessing step. So there is an influence on that, but overall they perform poorly in the majority of scenarios. Now, when we look at the median iteration time, the pattern becomes very straightforward. The generic compressors take a very small amount of time. Entropy is also very good. It's not the best, but it's comparable to zlib, which we had some related works in the past, taking this one as the best compressor in terms of time. So having entropy as close to it as we have, it does become a very interesting alternative for us to use without the need to generate the compressed files. The same scenario where the multimedia compressors take longer is also seen here. And to basically summarize this, that there is that correlation that I mentioned where low impact defects take longer to be detected, high impact defects take short amount of iterations to be detected. Overall, zlib and PPMD compressors are consistently good candidates, reaffirming previous works. They have a good response time. They also do not detect any false positives. They detect all of the defects. PNG showed good results in both effectiveness and efficiency, so it's also a very good candidate. Other multimedia compressors detected false positives. Moreover, Hive had the biggest median iteration time for all defects, but took fewer iterations to detect. So it could still be used in some scenarios where we have high impact, the expectation to have high impact defects that would take less iterations to detect. Moreover, entropy showed positive results, providing one of the quickest iteration time across all compressors, and it's comparable to zlib, what makes it a good solution, a good alternative for us to use in future work. To conclude, entropy is a viable and low-cost alternative to traditional compression for NCD within this use case. It's comparable, have comparable results to zlib. We could still use zlib, but if we're in a scenario where we don't want to generate the files in disk, we can opt for using entropy. PNG is also a good performance compressor, detected all anomalies without false positives. with 5 out of 7 response times below the median. Overall, the choice of compressor still needs to account for the constraints and priorities that we have on each use case. As I mentioned, Hive could still be an alternative solution if we're talking about effects that have high impact on performance. And definitely future works could explore this behavior on additional applications, with as well as alternating preprocessing strategies for multimedia, because those compressors that badly perform, they could also be improved with some additional strategies. And indeed, we need to take a look in depth at the false positive occurrences, because these could be treated as well. Thank you very much. I'm open to questions.
Thank you very much, Caio. So we don't really have much time for questions anymore, but let's see if, again, is anyone really
interested in?
Okay, listening. So is anyone wishing to make a quick question about this presentation? Okay, so thank you very much.
Thank you.
We're moving to the next presentation then. So our next speaker is Goran Link. So he's already there, I suppose. He is, all right.
Okay.
So Goran, are you ready?
Yeah, I'm ready.
Welcome to the session. So we're listening, so you can start. You need to share your time. Okay, so you need to share your presentation.
Just a second.
Okay, looking good.
By the way, I'm hearing my own voice, so yeah, thank you. Good afternoon, everyone. Thank you for being here. My name is Korhan Sevinç, and I study computer science at Top University and working in Roketsan currently in Ankara. Today I'm going to talk about my work, latent loss. It's a new way to train a text classifier for mental health texts. First of all, let me start with the why. Mental health is a big topic today. The WHO, aka the World Health Organization, and the European Union both say the same thing. We must find problems early. And here is the interesting part. People already show their feelings in text, in posts, in chats, in forums. This happens every day, also between doctor visits. But this text is difficult because it's short, it's informal. People do not write explicitly just like I'm depressed. They say it in an indirect way. You can probably tell that they're depressed, but you need to acknowledge their situation first. So we need models that understand this kind of text. And also one more thing, the model must be cheap to run because we want to use them all the time. And also we want to be able to accomplish this task with less GPU, VRAM, and quicker. So that was the goal, reach the quality of a big transformer model, but at a much lower cost. Our contribution is the training methodology. We call it dual latent GNet. It is a teacher-student method with a new loss. We call it latent G. The idea is simple to say, that the student does not only copy the teacher's answers, it also learns the teacher's inner features. It learns how to regularize itself like teacher, so it is not copying the teacher's answers, but it learns the distribution that the teacher answer is coming from. For the experiments, we joined 9 public datasets into one benchmark, and I will show you it on the next slide. And the result is our method beats a fine-tuned BERT model, but at the test time, it is only a small CNN. A few words about the data I want to say. We combine 9 public datasets, just like I said. The text come from posts, tweets, and short chats. Every text gets one of the 7 labels, as you can see on the right. Anxiety, normal, depression, suicidal, stress, bipolar, or personality disorder. All texts go through the same pipeline. First, we do the pre-processing, we clean the text. Then we use back translation for data augmentation, which is basically we translate the text from English to French and back to English. So we preserve the same semantic meaning, but we use it with different words for that particular sentence. So we got a richer data set, and this gives us more training examples and a good data augmentation. So this is the data set that we are working on with, and this was the pre-processing steps. Now it is time for the key idea. You probably know the knowledge distillation. A big teacher model trains a small student model. Normally, the student copies the teacher's output scores, so the student learns what the teacher outputs or predicts. Our idea is that is not enough, and we also want to know where the predictions live inside the teacher's feature space. We want that our student model learns how to regularize itself like teacher, so it is not copying the teacher's answers, but it learns the distribution that the teacher's answers. This is the key idea that I'm trying to emphasize. So if you could just look at the diagram on the right, the teacher is a CNN, a convolutional neural network with 2 training goals. We take its inner features and its output scores. Then we fit a Gaussian mixture model, a GMM, on this feature space. So now every class is like a cluster. And in the empirical studies that we have done, we generally think that it is the best practice that selecting the same number of Gaussian mixture models num-class parameter as the number of dataset classes. When we train the student also makes a feature vector. We find the best cluster for it, and we pull the student towards that cluster. So the student learns from 2 signals, the answer and the geometry of the feature space. The second signal is the latent G term in our name. To accomplish this, we deduce a new loss function, and we use cross entropy plus this information that I'm talking about as a classification loss, and mean square error as the reconstruction loss. Here is the full architecture. On the left, you can see the CNN backbone. It reads the text and creates a latent vector, the inner features. This vector goes to 2 different heads, 2 different decoders. The first one is the classification decoder, and it predicts the class. This was our goal. And the second one is the reconstruction decoder. It tries to rebuild the input. We have 2 goals because together they create a rich and useful feature space, a rich latent features. So classification alone is not enough. And with reconstruction, the features keep more information about the text. This model is our teacher and our student architecture. So we use this because its feature space is good enough to teach the student. Now here's how we train part. There are 3 simple steps actually. The first 2 steps are not the actual student's training, but we need a teacher model and its latent features plus the prediction logics, and we need to fit a Gaussian mixture model to them, so we can get the clusters. So let me start with the step 1. At the step 1, we train the teacher convolutional neural network, the architecture that I've shown in the previous slide, with its 2 goals: classify the text and rebuild the text. Both losses shape the feature space. And at the step 2, after the teacher is ready, we take its features and its output scores, put them together, we concatenate them into a single vector, and fit the GMM, fit the Gaussian mixture model on them. We do this only once before the student training. At the step 3, we train the student. For every text, the student makes its own vector for every text. We find the best Gaussian mixture model cluster for it, and we measure the distance to the teacher's feature. These two values, the cluster probability and the distance, form our loss function, latent G loss. And one more detail about the loss function. This loss becomes stronger during training. At the start, the student learns the basic tasks. And later, we pull it more and more towards the teacher's geometry. And by that, I mean by epochs, we are increasing the weight of the latent G component. So while the latent G component's weight is increasing, the reconstruction and all the other things' weights are decreasing. And if you need more detailed information on this, you can check the original paper. Now I'm going to talk about the experiments. Our experiments are simple and fair. We have one data set, the same train and test splits for every model, the same text cleaning, and the same data augmentation. So the differences come from the models, not from the data. And we compare 4 groups, classical TF-IDF models, which are classical machine learning algorithms and models like SVM and random forests. We compare CNN, RNN models, fine-tuned transformer models like BERT, Distelbert, Albert, and Roberta, and our dual latent GNet architecture. We measure accuracy, precision, recall, and F1 scores. And here are the results. The chart shows the best model of each group. The best classical model, random forest, reaches about 93%. The best RNN model, LSTM, reaches 94.1%. And our own teacher, the dual CNN, reaches 93%. The strongest transformer, fine-tuned BERT, reaches 94.83%. And as the orange bar, as you can see, our dual latent GNet architecture reaches 95.09%. It is the best of all groups. It is higher than BERT, just a little, and it is about 2 points higher than its own teacher. So the improvement comes from our training method, not from the CNN itself. The difference to BERT is small, but it's stable, and we can see it on accuracy, precision, recall, and F1 scores. And I want to talk about why this is important. Well, first, the scientific point. The teacher's inner features hold information, and sometimes the transformer misses that information. When the student matches these features, it gains accuracy on top of the answers. And second, later, the practical point. At test time, only the small student runs. There is no transformer, so you get transformer level accuracy at CNN costs. This is useful when you want to run the model often or on a small hardware. For the future work, we want to put a pre-trained encoder inside the student or the teacher and keep the latent G part. So we combine strong language features with our geometric training. And secondly, we want the model to show its uncertainty, not only a single answer. And we want to make it even smaller for devices with low resources. To conclude, latent G loss teaches a small model the inner features of a big one, and on mental health text, it reaches 95% above a fine-tuned BERT at low CNN cost. The code, the data, and the model files are on GitHub. You can see the link here. If you have any more questions, you can always contact me from this email. Thank you very much for your attention. I hope you will be having a nice day. Thank you.
Goran, thank you.
Yeah, I'm here.
Okay, so thank you very much. And let's see, any question? No? Okay, so it looks like we have no questions. So once again, thank you very much for the invitation. And we're moving now to the next presentation. So now we have Alexander Makarov. I think you're there, right? Yeah.
Good afternoon.
Okay. Do you hear me? Yes, we're hearing you. Can you share your presentation and we can start?
Yes.
Yes. Yes. Okay, looks good.
Do you see this
Do you see this?
right now?
No, I don't think we see what you expect us to see. Okay.
Yes.
We see
Can I
something.
start?
I guess you still need to click on the presentation button. At least from our side, we're just looking at all the slides, not presentation mode. Yes, let's see if it works. Excellent. Okay, let's go.
Good afternoon, dear colleagues. My name is Alexander Makarov, and today I'll present our work entitled "The Method for Automating Iterative Machine Learning Model Retraining on Event Streams in Decision Support Systems." The research is focused on clinical decision support systems, or CDSS, where machine learning models help doctors make better medical decisions. In this work, we consider cataract surgery and the task of selecting the optimal intraocular lens calculation formula. The main problem is that medical AI models become outdated over time. Clinical data is not stationary, diagnostic devices are updated, surgical protocols change, and the patient population also changes. Because of this, a model trained once may gradually lose accuracy. This problem is known as concept drift. In clinical practice, this is especially important if the model quality decreases, the system may give less reliable recommendations. Traditional retraining is usually manual or scheduled. It takes expert time, computational resources, and may react too late to sudden changes in the data. Therefore, we need an automated method that can update models iteratively, react to new patterns, and prevent degradation on standard clinical cases. The aim of this work is to automate iterative retraining of machine learning models in a clinical decision support system using a stream of events. The proposed method is called ECLA, Event-Driven Continual Learning with Anomaly Clustering. The method is designed to satisfy three criteria. The first criterion is non-degradation. After an update, the new model mustn't become worse than the previous one beyond an acceptable threshold. The second criterion is adaptability. The system must learn new clinical patterns as data accumulates. The third criterion is reactivity. The system must respond quickly when an anomaly appears in the data stream. The general scheme of the method is shown on these slides. The control object is the ensemble of classifiers used in the decision support system. The control system is the ECLA method. The method receives new clinical cases from the data stream and selects the necessary action: monitoring, local retraining, global retraining, or rollback. The key difference from scheduled retraining is that the update is not started only because a fixed date has arrived. It is started when the data stream shows that adaptation is really needed. After retraining, the new model is deployed only if the non-degradation condition is satisfied. Like Q new is greater than or equal the Q old minus epsilon. If this condition is violated, the system automatically restores the previous model version. Before retraining, clinical data must be prepared. In our system, medical examination protocols are processed automatically using OCR tools, include PyTesseract. Then raw medical data is transformed into one structured patient level record. At this stage, raw medical data is transformed into one structured record for each patient. If several devices measure the same parameter, the system selects the value by device priority. or if priority is equal by the latest examination date. This prepares clean and consistent data for machine learning. This slide shows the patient type parameters used by the model to decide which IOL calculation formula is suitable. The decision support framework includes separate binary classifiers for different IOL formulas. The system gives information about formula applicability, but the final decision remains with the doctor. So the system doesn't replace the medical expert. It supports the doctor, especially in difficult and non-standard clinical cases. We compared ECLA with common retraining approaches. Manual periodic retraining is simple but slow and expensive. Cron-based retraining is automatic, but it still works by schedule and doesn't analyze nullity. Grid search can improve model parameters, but it is computationally heavy and doesn't provide fast response to anomalies. MLOps retraining pipelines are closer to our approach because they include monitoring, validation, and deployment. However, they usually do not provide explicit routing of new patterns into anomaly clusters. ECLA, nullity detection, clustering, local adaptation, validation, and rollback in one event-driven life cycle. Now, I will describe the method more technically. For each incoming clinical case, the method checks whether this case belongs to the standard data distribution. If the case is standard, the system continues monitoring. If the case is statistically unusual, an anomaly event is generated. However, the model is not retrained after every single anomaly. One isolated outlier may be noise, measurement error, or a rare individual case. Therefore, the anomaly is first routed to a cluster of similar anomalies. Only when a stable cluster is accumulated, the system starts local retraining using the learn local expert procedure. This slide shows the nullity clustering mechanism. Each anomalous case is assigned to the nearest anomaly cluster using the Mahalanobis distance. If the distance to the nearest cluster is below the acceptable threshold, the case is added to this cluster. Otherwise, a new cluster is created. And local retraining starts only when the anomaly cluster reaches the threshold nth, which is selected in the range from 33 to 50 cases. The lower bound is defined by the feature space. We use 32 input parameters. So for stable covariance matrix estimation, we need at least d+1 observations. That is 33 cases. If the cluster is smaller, the covariance matrix may become degenerate and Mahalanobis-based processing becomes unreliable. The upper bound is limited to 50 cases because after this point, additional accumulation gives less benefit for continual learning. The new pattern may become blurred or mixed with other nullity types. So the range 33 to 50 gives a balance enough data for stable statistic, but still a compact cluster for learning one specific new clinical pattern. The method uses the following event priority. An anomaly has the highest priority because it may indicate a sharp data shift. Accumulation is the second priority because retraining starts only after a stable microbatch is formed. The time event is a safety mechanism if no anomaly cluster reaches the threshold for a long period. A global retraining can still be started. This hierarchy helps avoid unnecessary full retraining and use computational resources more efficiently. For anomaly detection, we use the Mahalanobis distance. This metric is suitable for ophthalmological data because the features are correlated. The Euclidean distance treats features as independent and equally scaled, which is not correct for this domain. Mahalanobis distance uses the covariance matrix. It evaluates how unusual the whole combination of parameters is not only one separate value. This is important because some I parameters may look unusual separately, but normal in combination with other parameters. The anomaly threshold is derived from the chi-square distribution. This gives a statistical interpretation of novelty detection and allows us to control the false positive rate. In our study, the threshold is selected so that no more than about 1% of standard cases are incorrectly classified as anomalies. After local retraining, the main risk is catastrophic forgetting. The model may learn new anomalous cases, but lose quality on standard cases. To prevent this, ECLA uses two mechanisms. First, elastic weight consolidation, or EWC, protects the weights that are important for previous knowledge. Second, experience replay mixes the new anomaly cluster with historical examples. In our implementation, historical cases make up about 15 to 20% of the training batch. This helps the model learn new patterns while keeping stable performance on old data. The method was tested on real ophthalmological data. The dataset contains 70,421 clinical cases collected from 2018 to 2025. The data was split into training and fixed test subsets. The test set was not changed between iterations or methods. We performed 10 independent runs with different initial ensemble states. Initial accuracy values ranged from 0.77 to 0.83. At each iteration, we measured accuracy, AUC, forgetting measure, and time to recovery. We also applied the Mann-Whitney U test to check whether the quality improvement was statistically significant. The experimental results show that ECLA outperforms all baseline methods. At the final point, ECLA achieved accuracy of 0.89 and AUC of 0.873. On the AUC graph, ECLA shows stable growth while manual training and cron and grid search reach a plateau earlier. The learning curve also shows the stable behavior. Train and test accuracy grow together, and the convergence gap is only 0.027, which means there is no clear overfitting. The reaction speed is also better. The median time to recovery is 1.2 days for ECLA compared with 7 days for cron and grid search, and 14 days for manual retraining. So ECLA gives better quality and reacts faster to changes in clinical data. The statistical test confirms that the improvement is not random. At the first iterations, the effect is not significant because the system hasn't accumulated enough anomaly clusters. Starting from later iterations, the Mann-Whitney U test shows statistically significant improvement. In the final comparison, all 10 final model states are better than the initial states. This supports the conclusion that the method provides stable improvement over time. The achieved results confirm the main hypothesis. The method is iterative because model quality improves over time. It satisfies non-degradation because each update is checked before deployment and rollback is available. It satisfies reactivity because anomaly-based updates are much faster than scheduled updates. It satisfies adaptability because new patterns are accumulated in clusters and then used for local learning. Finally, it is resource efficient because local training depends mainly on the anomaly cluster size, not on the full dataset size. From the practical point of view, ECLA changed the maintenance process. Before automation, full retraining on the growing data set required about 25 hours and was usually performed once every 7 days. With ECLA, global retraining remains only as a safety option. The main update mode is local adaptation, which usually requires from 2 to 12 hours, depending on the cluster and model configuration. This reduces expert involvement, lowers downtime, and decreases the risk of human error. The main practical idea is simple. The system learns more often, but in smaller updates and only when the data stream provides a reason. To conclude, we propose then ECLA method in CDSS. The main contribution is the unified life cycle, anomaly detection, anomaly clustering, local continual learning, non-degradation validation, and automatic rollback. The method was implemented and tested in the ophthalmological CDSS for cataract surgery. The experiments on real clinical data showed high accuracy, higher AUC/ROC, faster reaction to data changes, and lower resource cost compared with the baseline retraining approaches. Although the current application is IO formula selection, the framework is domain independent and can be adapted to other medical decision support systems with non-stationary data streams. Thank you for your attention. I'm ready to answer your questions.
No, it was really struggling with time. So thank you very much, Alexander. And we're now moving to Fatwa Al-Bakari. I think you're there, right?
Yeah.
Also, welcome. And if you're ready, you can start sharing your presentation.
Thank you.
Okay, we're starting to see something. Looking good. Excellent. So you can start.
Okay. Hello everyone. My name is Fadwa Bakari, and I will present our study on evaluating an analytic speech recognition system in a noisy environment using MFDWC features. So, automatic speech recognition for Amazir is increasingly needed, especially for e-learning platforms and voice-controlled applications. However, this is a challenging task for two main reasons. First, there is a real lack of speech resources for the Amazigh language. Second, recognition performance is strongly degraded by environmental noise and by speech variability, like gender, age, native or non-native speakers. And there has been growing research interest in Amazigh automatic speech recognition, but most of this work has focused on the Tarifit dialect. Our study instead targets the Tashahit dialect spoken in the Agadir region. Most existing systems rely on MFCC as their feature extraction method. However, MFCC is known to be sensitive to noise, mainly because of the DCT that relies on has a uniform time frequency resolution. To improve efficiency, MFCC is often combined with dimensionality reduction techniques such as PCE. So, in contrast, the discrete wavelet transform, or DWT, offers better time frequency localization and requires less storage, which makes it more suitable for noisy conditions and for systems with limited memory. So our proposed solution combines NFCC and DWT into a single feature extraction method called MFDWC in order to improve robustness in noisy environments. And our proposed Amazir automatic speech recognition system is built around three main steps: pre-processing, feature extraction, and classification. So let's go through each of them. For pre-processing, we combine two techniques, the zero crossing rates and the short-term energy. Together, these two methods provide an effective way to detect both activity and silence within a vocal signal, which allows us to the silent segments before feature extraction. And the following figure presents the speech signal of the Amazigh word Azul, that means hello in English, before and after using the zero crossing range and short-term energy method. So the first step of feature extraction is the pre-emphasis filter. This is a high-pass filter applied to the input signal used to boost the high-frequency competence and reduce the low-frequency energy before framing. And next, the signal is split into frames of 25 milliseconds with 10 milliseconds of overlap. Each frame is then multiplied by a humming window to avoid discontinuities at the edges of the frame. And finally, we apply the FFT to convert each frame from the time domain to the frequency domain. And this figure shows the framing, windowing, and FFT steps. After the FFT, we apply a mil filter bank, which is built according to the mil scale, since this scale better reflects human auditory perception. And in our system, we use a filter bank composed of 25 triangular filters. And here you can see the conversion from the linear scale to the mil scale. And this figure shows the mil filter bank. And then we apply the discrete Fourier transform method to the logarithm of the mil filter bank and use the Dapshi's wavelet as the mother wavelet, which produces a final set of 11 NFDWC features per frame. And now let's move to the classification step. We selected the SVM as our classifier. So SVM offers several advantages for our application: high accuracy, robustness to noise, and efficient decision making. However, SVM supports binary classifiers, so multi-class problems like ours with many letters, digits, and words needs a decomposition method. So two main methods are commonly used for this: one versus all and one versus one. In the one versus all method, each class is treated as the positive class against all other classes combined as negative. So this requires training key binary classifiers for key classes. And in the other hand, we have also one versus one method. So one versus one requires more classifiers overall, but each one is trained a fewer samples and solves a simpler two-class problem. In practice, this often makes one versus one faster and more robust for multi-class classification, which is why we adopted this method in our system. And before presenting our database, let me give a short introduction to the Amazigh language. So the Amazigh belongs to the Afro-Asiatic language family, and it is spoken across North Africa, in Morocco, Algeria, Libya, etc. And in Morocco specifically, there are three main regional dialects: Tashilhit is spoken in the High Atlas and Southwest, Charif is spoken in the north, and Tamazight spoken in the central and southeast regions. So now let's look at the database we built for the study. We created a dedicated Amazigh speech database for training and testing our system. Our previous work used a dataset of 33 letters and 10 digits recorded in a calm environment. For this study, we extended the dataset to 53 isolated units, in total 33 letters, 10 digits, and 10 isolated words. And the following table presents the 33 Amazigh letters. And table 2 presents the 10 Amazigh digits from 0 to 9. And table 3 shows the 10 isolated words for the Amazigh Tashilhit language. So all the data was collected from 120 Moroccan speakers, 16 native speakers from the Agadir region, and 16 non-native speakers. In total, our dataset contains 63,600 recordings. And the dataset was recorded under two different conditions: a calm environment, personal office, and a noisy environment recorded in a cafe. And this table shows our first 4 experiments conducted in the calm environment. We tested recognition on the 33 letters, the 10 digits, and the 10 words, and finally on the full combined set. We repeated this exact same 4 experiments under noisy conditions. Let's now look at the results, starting with the calm environment. For 33 letters, NFDWC method reached 88.52%, and for the 10 digits, NFDWC achieved 93.06%. And for the 10 Amazigh Tashilhit words, NFDWC achieved 94.67%. And finally, on the full combined dataset, 33 letters, 10 digits, and 10 words together, NFDWC achieved 90.37%. So across every configuration in the calm environment, NFDWC consistently outperforms both NFCC and DWT. Now let's move to the noisy environment, which is the main focus of this work. For 33 letters, FDWC achieved 71.15%, and for the 10 digits, FDWC achieved 78.83%, and for the 10 Amazigh Tashilhit words, FDWC achieved 77.22%, and on the full combined dataset in the noisy environment, FDWC achieved 73.55%, and these results clearly confirm that NFDWC is significantly more robust to noise than NFCC alone, and constantly better than DWT alone as well. And the following table presents the results obtained by other systems and by the proposed system. So to conclude, we proposed an Amazigh speech recognition system built on an expanded database of 63,600 recording covering 33 letters, 10 digits from 0 to 9, and 10 Amazigh Tashilhit words recorded in both calm and noisy conditions. Our preprocessing step is on zirconium and short-term energy. Removes silent segments and compresses the signal, improving overall efficiency. And our proposed NFDWC features combining NFCC and DWT provide strong robustness to noise. And for classification, we used the SVM with a 1 versus 1 method, which proved effective for multi-class separation. Overall, our system achieved 90.37 accuracy in calm conditions and 73.55% in noisy conditions, outperforming both MFCC-based and DWT-based method individually. These results confirm the effectiveness and the robustness of the proposed MFTWC architecture for Amazigh speech recognition. And this is the references. And thank you for your attention.
Okay, thank you very much.
Thank you.
So, are there any questions for Karim? No? Okay, so we have no questions. So thank you very much, Karim, for your presentation.
Thank you. Thank you very much.
Now we're moving to our last speaker, Sérgio Freitas. Sérgio, are you there? Okay.
Sorry, sir. I'm here.
You're there and you're ready.
Yeah.
Good. Yeah. Okay, so whenever you want to begin, just.
Are you seeing my?
Well,
Yeah.
maybe not what we should be seeing.
I will try to change the. So just a moment, please.
Okay.
Okay.
That sounds good. Yes. Okay. So get started.
Good afternoon. My name is Sérgio Freitas. I'm from University of Brasilia, and today I'm going to present our work, an heterogeneous ensemble meta model for languages large-scale categorization in Portuguese scientific records in Oasis BR. This is a collaborative study with some students and researchers. André, Milena, and Rina are students, and Washington is a researcher from IBICT. This is a practical problem in scientific repository, that is, how can you categorize a large volume of Portuguese scientific metadata in a reliable form, but using the CAPS. CAPS is in Brazil, is our research foundation institute that have a taxonomy of great areas, broad areas to classify research. The central idea is that we are not just a text classification experiment. It is a repository scale information service. We will notice that our intent at the beginning of the research is to find people that can help in some areas, like reviewers and researchers that could be working some project, and not just a classification problem. We will first explain the problem, why the problem matter, then describe them. And sorry, I have some problem here. That's okay. And describe the effects. The motivation starts with scale and multiple or heterogeneity. Our corpus, OSBR, is approximately 1.6 million scientific records from multiple sources, various sources, including institutional repositories, journals, digital libraries, and scholar information providers. It's a Brazil open source, open access portal for aggregate scientific publication. It's very important to us because you have all the publication from our 160 public university plus 19 private university publishing their work here. Theses, master theses, and open journals are put all the stuff here in the OASIS repository. So you have a large repository, not published in vehicles, in journals, but available, publicly available for everyone. At this scale, topical categorization became a service layer. Like I said like I said before, you can find researchers and also reviewers that are using or that are publishing or working in some areas. It influences how users retrieve records, how repository manage monitor content, and how scientific production can be analyzed by a broad area of knowledge. The second element that you see is the CAPS taxonomy. Né? In Brazilian research and graduate education ecosystem, Brasilia CAPS broadcast areas provide a relevant classification structure for evaluation, aggregation, and also for policy reporting and funding research, of course. The third element is operational risk. A simple classifier may not work well under some benchmark curated conditions, né? But it can also become breeding with abstract as sparse metadata fields are inconsistent and vocabulary varies across institutional and disciplines. This is the reason why you have a lot of variation of the terminology, maybe depends of course of the area. If you are looking at, for example, literature or engineering or biology and things like that. So the question is not only, can you classify scientific records? This is not the only problem. The question is, the more practical question you establish is, can you build a categorized strategy that remains robust under the deployment-like conditions, né? And so we state that our objective of the research is automatically assigned OASIS records to one of the 9. You have 9 areas in CAPS, né? And using only text or metadata, specifically in the title, abstract, and keywords. You don't have the whole article. The core proposes an international assembly model instead of selecting only one best classifier. The system combines several learners through performance-informed weight voting. The weights are derived from the benchmark. You use the F1 scores. So strong models contributes not only to a final decision, but to assembly still preserve complementary behavior from different learners. The contribution are divided in 3 parts. First of all, we reframe the original active project as a reproducible scientific classification pipeline. Then you compare 8 basis learners and define a simple but conservative meta model. And finally, we explicitly separate curated benchmark evidence from operational behavior. This is just a slide that summarizes that. Now you have about 1.6 million, about 800,000 are pre-labeled. Of course, the rest are not labeled, and we are using 9 CAPS broadcast broad area, sorry. So what you did? You reconstruct, this is our pipeline. First, you have metadata ingestion at the system. Then you use some natural language processing to lemmatize all the things. Né? This is a part that we are not putting here in the work, but it's very interesting. Né? And this is what you can transform our space, original space of 200,000. Sorry.
We're not seeing anything at the moment.
Oh, not seeing, sorry. Sorry.
Okay.
I try again. Sorry, I try again. To me, it's presenting.
No problem.
It's interesting. Now, okay. Okay, thank you. Sorry, Rui. This part, lexical normalization and feature consolidation, is very important, but we did not rate them here at this paper. First, it's the reason why you reduced from 200,000 words to only 3,140 features, words. No? You use a very interesting natural language processing strategy that can reduce this space. And this space is the key feature of the whole thing that we are presenting. Well, then we use a Berry learning that you already said. There are 18 Berry learning use, for example, random forest, XGBoost, CatBoost, SVG, regression, Gaussian, decision, and AdaBoost. And all this base learning, you have putting the results on a weighted voting that are pre-trained. You pre-trained every corpus, subject corpus, pre-labeled corpus in the areas. So you have how to say, you can compare how well they are performing in each area. Then first, and then you categorize using the CAPS label. This is the 8 learners. They use the conservative aggregation, no stack, just a class probabilistic and aggregation using the FIM score. This is the way that we aggregate our that we aggregate our preferable models that we use. And that's using the FIM score, no problem. Are you trying to? Okay. Then, and this is the result, the standard alone. You notice that the XGBoost and the random forest both obtained a good result. CatBoost may be a little and less, but SVC you have a lot. And logic regression and Gaussian decision trees and AdaBoost, you don't have anything good. So you use more, the more you use are the first 2 ones. Sorry. XGBoost, like I said, XGBoost and random forest are the best one that you use. You select them using the FIM score because it have about 0.753 factor that are very interesting to us. Of course, you have to say that using a broad corpus like OSBR that comprise not only one type of language, not on one type of computational or greater knowledge, greater area. There is a lot of change between one language, one corpus, subcorpus to another. So this is a very interesting result that you obtain because it maintains all the performance based only on the features that you have established. Well, finally, operational scene evaluation. This is results that to see how you can performance across the 9 great areas. I have to say that the last one that was multidisciplinarity, it's very interesting one because nowadays you don't have only research applying to one area. Normally you have, for example, bioinformatics that use biology, but also exact language that here are informatics. You have 2 areas that are interacting to produce a paper, to produce a research. And but also you have, for example, education and engineering, engineering education that is very interesting. And also the last one that is you cannot classify them as being one area, not in another area, but multidisciplinary. That is a very side effect, very side interesting results that you have obtained in this research. And what change in deployment? First of all, we'll have the deployment comparison shows a clear shift. The select simple model baseline achieved on average base reach, the assembly model increase our value. So you have looked that the assembly model are getting better results than the single model. This value should be not confused with the F1 score from the current benchmark. They refers to a different and hard evaluation setting, curating benchmarks, estimated relative model, qualify under more controlled conditions. Operational brains are closer to actual repository use. You have to say this is also implemented. This strategy is inside a repository by a public institution Brazilian, and this is called Contextus. Contextus is where this whole process is implemented, and it also comprises all the Oasis BR metadata, but also other like Oasis and so on. In development records can contain noisy keywords, missing abstracts, short files, ambiguity, terminology, and so on. That's the reason why you use the reduction of the features. It's a very interesting because you use a synonym-aware features. You reduce all the words that are using to classify in one specific area using the most salient words that appears in this one. You have to state here that you are not using like transformers, try to things like that. You are categorizing. In categorizing corpus, you just want to seek which is the best classification. So, the conclusion, metadata engineering is decisive. Random forest and XGBoost is very strong learners, standalone learners. The assembly improved the professional read across every CAPS data. So you have published this material on the system. Like future work, you are trying to see if transformer you will get better results or not, but this is an ongoing research. Well, that's all. Thank you all. Here's our contact. You are open to question. Thank you.
Thank you, Sergio. So any questions from the audience? No, they're very quiet today. So let's close the session. I'd like to thank all the speakers, Caio, Faran, Abakarim, Alexander, and Sergio. I forgot anyway. So thank you all for your presentations, and hope you enjoy the rest of the conference.
Thank you.
Thank you. Thank you very much. Thank you all.
Bye-bye.
Bye-bye.